Hello everyone. Today we're going to talk about electric current. How is electric current made? Dozens of sushi dishes ride along a conveyor belt in figure 1, as you can see right there. The conveyor belt carries full dishes past customers and carries the empty plates back to the kitchen. We might be wondering what a conveyor belt of rice, vegetables, and fish could possibly have to do with electricity. Like the sushi plates, electric charges can be made to move in a confined path. Flow of electric charges. Lightning releases a large amount of electrical energy. However, the electric charge from lightning does not last long enough to power your radio or your TV. These devices need electric charges that flow continuously. They require electric current. Recall that static electric charges do not flow continuously. When electric charges are made to flow through a material, they produce an electric current. Let me say that again. When electric charges are made to flow through a material, they produce an electric current. Electric current is the continuous flow of electric charges through a material. The amount of charge that passes through a wire in a given period of time is the rate of electric current. A unit for the rate of current is the ampere, named after André Marie Ampere, an early investigator of electricity. The name of the unit is often shortened to amps, or capital A. The number of amps describes the amount of charge flowing past a given point each second. Here in figure 1, the conveyor belt represents a current. If it is represented a greater current, more plates would pass by you in the same amount of time. One way for this to occur would be for the belt to go faster. Current in a circuit. The electric currents that power your computer and music player need a specific path to work. In order to maintain an electric current, charges must be able to flow continuously in a loop. A complete unbroken path that charges can flow through is called an electric circuit. Someone jogging the roads in figure 2 is moving like a charge in an electric current. That's this right here. It is a continuous path that is not broken. If a road forms a complete loop, the jogger can move in a continuous path. However, the jogger cannot continue if any section of the road is closed. Similarly, if an electric circuit is complete, charges can flow continuously. If an electric circuit is broken, charges will not flow. Electric circuits are all around you. All electric devices, from toasters to televisions, contain electric circuits. How do conductors differ from insulators? You can safely touch a rubber coating on an appliance cord. If you touched the wire inside, you'd get shocked. That's because charges can flow more easily through some materials than others. A conductor is a material through which charges can flow easily. A conductor can conduct the flow of electricity. Electrons can move freely, allowing conductors to be charged by induction. Metals, such as copper, are good conductors. This is why current-carrying wires are usually made out of metal. Copper is a high-quality conductor for electricity. Wires are surrounded by insulators. Insulators are materials such as rubber that do not allow charges to flow. However, electrons can move around within their own atoms, allowing for polarization. They can also be stripped off when charging by friction. The difference between conductors and insulators comes from how strongly electrons are attached to atoms. The atoms in conductors have loosely bound electrons that can move freely. Let me say again, The atoms in conductors have loosely bound electrons that can move freely. Electrons in insulators cannot move freely among atoms. What affects current flow? Suppose you're on a water slide at an amusement park. You climb the steps, sit down, and whoosh. The water current carries you down the slide. Electric charges flow in much the same way water moves down a slide. Current flow is affected by the energy of the particles. Current flow is affected by the energy of the charges and the properties of the objects that the charges flow through. Again, current flow is affected by the energy of the charges and the properties of the objects that the charges flow through. Water currents. A completely horizontal water slide won't be much fun. A water slide that was only a few centimeters tall wouldn't be much better. Water slides are exciting because the gravitational potential energy, remember that gravitational potential energy is the energy of an object has because of its height above the ground. So in other words, the higher it is, the more gravitational potential energy it has. As the water falls down the slide, its potential energy is converted to kinetic energy. Remember, kinetic energy is energy of movement. The water speeds up since speed increases as kinetic energy increases. The higher the slide, the more potential energy the water starts with, and the faster it will end up moving. At the bottom of the slide, the water has no potential energy. It has all been converted to kinetic energy. The water gains potential energy as it is pumped back to the top, starting the ride again. Electric currents. Electric currents flow through wires like water through pipes. Charges flow because of differences in electric potential energy. Potential energy from an energy source, like a battery, gets converted into different forms of energy. If a circuit contains a light bulb, its potential energy is converted into light and heat. Specifically, light and heat energy also known as thermal energy. The charges flow back to the energy source and the process restarts. Slides convert gravitational potential energy into kinetic energy. Voltage. The V on a battery stands for volts, which is a unit of voltage. Voltage is the difference in electrical potential energy per charge between 2 points in a circuit. Electric potential energy per charge is also called electric potential energy. This energy difference causes charges to flow. Because the voltage of a battery is related to energy per charge, it doesn't tell you how much total energy the battery supplies. A car battery and 8 watch batteries both supply 12 volts, but 8 watch batteries can't run a car. Each charge has the same amount of energy, but the car battery can provide that energy to many more charges. Let me say again. Each charge has the same amount of energy, but the car battery can provide that energy to many more charges. This results in a higher energy total. You compare voltage to gravitational potential energy per kilogram. Figure 4 shows the difference between total energy and energy per kilogram, which is here. The total electrical potential energy has a charge. The total electric potential energy a charge has depends on voltage. Just as gravitational potential energy a person has depends on his or her height above the ground. Total gravitational potential energy is the energy per kilogram times the number of kilograms. The total electrical potential energy is the energy per charge times the number of charges. So you've got some comparisons here. Resistance. The amount of current in a circuit depends on more than voltage. Current also depends on the resistance of the circuit. The resistance is the measure of how difficult it is for charges to flow through an object. The greater the resistance, the less the current there is for a given voltage. The unit of measure of resistance is an ohm, and it is a Greek symbol. It also looks like a horseshoe. Remember, that's the symbol for ohms, which is the unit of measure for resistance. 4 factors that determine the resistance of an object are diameter, length, material, and temperature. Objects with different characteristics have different resistances. If more than one path is available, more current will flow through the path that has a lower resistance. This concludes our reading for electric current. Thank you. Goodbye.